You are almost done with the course. You have now learned about the classical model in detail and applied it to real case studies. You have seen numerous applications and got to work with the IDEA protocol. But are there other settings which are suitable for expert judgment? And if so, which methods are then appropriate to use? During this extra module, you will get the chance to learn about all these. Recall that the classical model, as you have learned it, aims to quantify uncertain quantities. The uncertain quantity may be the percentage of India's population resistant to antibiotics by 2025, for example. The inherited uncertainty of this unknown quantity is modeled with a continuous distribution. Therefore, all questions, both of interest and calibration, are regarded as continuous random variables. This is the classical model in its standard setting. But the classical model can also be applied to discrete random variables, and especially to binary or Bernoulli random variables. That is, variables which can take two possible outcomes. For example, it will rain or it will not rain tomorrow. In this case, the uncertainty is quantified by estimating the probability that it will rain or the probability that it will not rain tomorrow. One can elicit such probabilities from experts and employ what is known as the classical model for discrete random variables. When considering more than one random variable, one can account for the existing dependence between these random variables. Various correlation coefficients, such as the Spearman or the Pearson correlation, can capture the dependence and can be computed from the data at hand. But when data of one random variable is missing, the dependence would then have to be elicited using expert judgments. This can be done by using the so-called exceedance probabilities. That is, the probability that one variable is above its median, given that the second variable is above its median. The last topic brings us to the core of decision theory. Decision theory provides a model for rational decision-making under uncertainty. The model involves defining the decision space for all possible actions, quantifying the uncertainty regarding the true but unknown state of the world, as well as quantifying the values of possible outcomes of actions. Having this input allows us to evaluate the expected value of each possible action and choose the action with the highest expected value. For individual decision-making, this model describes rational decision under uncertainty, which has been formalized by Savage. Dealing with highly complex and structured decision-making settings involves taking into account the opinion of different groups and different stakeholders. The decision-making model involves then specifying a group uncertainty distribution over possible states of the world, as well as a group valuation of the outcomes. We have seen how to obtain the group uncertainty distribution using the classical model. That is just the distribution of the best performing decision maker, which is usually the performance-based decision maker. The group valuation, or the stakeholder preference, implies a different type of elicitation that is generally known as preference elicitation. In order to understand what preference elicitation means, let's consider a simple example. Suppose we aim to capture a group's preference about the most preferred social media platform by people with ages between 20 and 25 years old. How to elicit experts' preference along with the aggregation of the individual preferences will be detailed in a future video. Oh, by the way, which is your most preferred social media platform? Thank you for your attention and enjoy learning about these extra methods.